Hello everyone, welcome to Anupal sir's video classes. In this video, I will discuss some important thing regarding solid, the defects of solid, doping, and the problem and conceptual question related to basic solid chemistry. Okay. So why different types of defect arise in case of solid state? Because a solid is a perfectly crystalline solid when it is present in 0 Kelvin. I have told you earlier classes. But when we increase the temperature, then heat energy is provided, then some defect will arise due to different types of motions, vibrations, increase in kinetic energy. And this defect can be classified into electronic defects, atomic defects. Electronic defects means in this case no shift of atoms arise. Okay? Only loss of electron occurs, positive holes will be created, and thereby it is known as electronic. But in case of atomic defects we have stoichiometric and non-stoichiometric. Stoichiometric means where the ratio of positive and negative charges, that is the ions, before defect, after defect, their ratio remains same. But in non-stoichiometric defects, the stoichiometric defects, that means the ratio is not same. But remember one thing, that is in case of stoichiometric or non-stoichiometric, the total charge must be balanced. Okay. So stoichiometric can again be classified as Schottky, can again be classified as Frankel. Schottky means where, suppose a perfect crystalline solid is there, okay, at low temperature, but with rise in temperature, what is happening? It may happen that from some of the crystals, this A plus at any position, it may happen from any position, this A plus and this B minus are removed from the original crystal. So before the defect, if the ratio was 5:5, say for example, and after the defect the ratio becomes 4:4, the ratio remains same. So it is known as Schottky defect. But in case of Frankel, if we come in the Frankel defect, then the original crystal was like this before defect, but after defect it may happen that one of the A plus has lost its original position and occupied the interstitial gap. But it is again, this A plus is not removing, this A plus is present within the crystal but at the interstitial gap. So the ratio remains again same and total charge is also balanced. So that is known as stoichiometric. This type of defect is known as stoichiometric and it is known as Frankel defect. Next come to the metal excess part. Non-stoichiometric means it has two probability, namely metal excess and metal deficiency. So metal excess again can be classified as metal excess, that means loss of anion can be possible. So one is anion vacancy and another one is extra cation occupying the interstitial gap. So before defect, if it is A plus B minus like that, A plus B minus A plus like that, crystal atoms are present. Metal excess, that is anion vacancy, what is happening in this case? In this case, when in the crystal some extra metal is present, that means there is a possibility of some metal to occupy or to get adsorbed on the surface of the crystal. So then what is happening? One of the B minus ions can be removed from its original position and it may get attached to the newly comes atoms. So this portion is vacant, but I have told you that stoichiometric or non-stoichiometric, for both the cases vacancy or total charges must be balanced. So here within the crystal number of plus is more than number of minus, so total charge is not balanced. That is why to maintain electrical neutrality, what is happening here, 1A losing one electron to this part, and when energy is provided, then this electron can be emitted, can be excited from lower energy state to next higher state, and when that electron returns, then energy will be emitted, and that portion is responsible to give us flame test. So we see different types of colors. That is why this center is known as Farabi center. Here F center. Farabi means color. So this center is known as F center. Now the second part is metal excess, anion vacancy we have done. Next is our extra cation occupying the interstitial gap. Okay. So in this case, what is happening? All the crystals are there, like in orderly arrangement, but some of A plus may come from any other crystal and occupy the interstitial gap when heating energy is provided. It is observed in case of ZM. Okay. Then to maintain electrical neutrality, some of the B minus also removed by losing electron here to maintain electrical neutrality. So that is why here number of A plus in this type of defect is more than number of B minus, but the total plus charge and total minus charge is same. That is why it is known as metal excess, but that is known as extra cation occupying the interstitial gap. The next one is metal deficiency, where metal portions will be deficient in nature. So in this case, what is happening? Metal deficiency means its sub-classification what will be? That means cation vacancy and extra anion occupying the interstitial gap. Cation vacancy, what is happening in case of cation vacancy? One of the cation may be removed from any position. Okay, so here vacancy has been created. That means total A plus and B minus is not same. That is it is why non-stoichiometric. But in this case, suppose one of the A plus is getting di positive charge. That means here total plus charge and total minus charge is getting balanced. So this type of defect will be observed in case of those metals which have some variable valency, like iron, like nickel, like copper, like mercury. And the last one, that is when crystals are orderly arranged but metal deficiency, that means extra anion occupying the interstitial gap. So from any adjacent portion, any anion may come to occupy the interstitial gap, and to maintain electrical neutrality, some of the A plus will become di-positive charge to maintain electrical neutrality. But among all those defects, the metal deficiency due to extra anion occupying, this portion is very uncommon. Why? Because this interstitial gap is very short. So to occupy the interstitial gap, that is easier for a cation but not for an anion. That is why it is very much uncommon defect. Metal deficiency due to extra anion occupying the interstitial gap is not a common case. Now come to the doping part. That is, we know when electronic transition occurs from valence band to conduction band, then what is happening? Then different types of conductivity, heating conductivity, electricity, these are generated. So in this case, doping, silicon, germanium, they have their valence shell electrons. How much? They have their valence shell electrons, that is 4. But when they are doping with some pentavalent means like phosphorus, like arsenic, this type of pentavalent elements, then what is happening? Then due to presence of extra electron, these have the ability to conduct electricity, or they have developing conductivity property. That means they are known as N-type. Why N-type? Because when silicon, germanium, they are doped with pentavalent, that means due to extra electron, that means negative charge, due to negative charge, they have the developing property to conduct electricity. That is why they are known as N-type. But when they are doped with trivalent something like boron, like aluminium, they are doped with trivalent something, that means P-type, because they have trivalent, but silicon, germanium, they are having the property to have tetravalent. That is why a positive hole will be created, and therefore they are known as p type. Okay. Now come to this type of problem. Okay, this is a diagram where the box red portions indicate M and the blue portions indicating X. Okay, occupied by X. Then the question is there, what is the formula of this crystal? So if M is present at the edge centers and the middle, then what will be the contribution of M? That is, due to the middle portion, it will be pure 1, and from edge we know 1/4 contribution is there, so it will be 4 into 1/4, that means M will be 2. And here X ta koto hobe? What will be the value of X? X will be, that is here 1/8 into 8 corners and 6 faces are there. This is one face, this is one face, this is one face, this is one face, this is front face 1 center, and in the back face 1 center. So for X it will be 8 into 1/8 plus 6 into half. So it will be 4. That means the formula becomes M2X4. So we can write it MX2. That is why option B is the right answer. So now come to the concept of void. That is, void can, the main numericals, that is based on tetrahedral void and octahedral void. Numerical comes on this part. Okay. So tetrahedral void means what? 3 balls are there. 1, 2, 3. Another ball is on the above face. And again 3, 1, 3, 1, like that. So this atom, this blue atom, okay, is responsible for the formation of 2 voids basically. One is below, another is above portion. So remember the trick, when n atoms are there, remember the trick, when n atoms are there, then tetrahedral void will be 2n. And here that is octahedral void. This portion is void, octahedral. That means 6 atoms are there, 1, 2, 3, 4. Another one is above the plane, another one is below the plane. So therefore here 2 atoms the contribute 1 void. That means 1 atom contribute 1, because in the below portion, lower portion, and again in the above portion. That means if n atoms are there, then this is called tetrahedral void, and n, this is called octahedral void. Okay. So depending on this concept, we need to solve a numerical here. That this question says that total number of voids in 0.5 mole of a compound forming hexagonal close packed structure. Total number of voids in how many moles? In 0.5 moles having hexagonal structure. So as the structure having hexagonal, that means how many atoms are there? 6. Okay. So for 6, how many octahedral voids are there? 6 octahedral voids. And how many tetrahedral voids are there? For 6 atoms, how many tetrahedral voids are there? That is 6 into 2. So it will be tetrahedral void, that means 12. So total number of void becomes how much? Total number of void becomes 18. Okay. So therefore 18 voids are formed by 6 atoms. So for per atoms the void will be 18 by 6, that is 3. So 1 mole compound contains how many atoms? Avogadro. 1 mole compound contains Avogadro number of voids. So therefore the total number of voids in 1 mole, that would be these 3 multiplied by this term, 3 into n. And therefore 1 mole if this, then 0.5 mole will be how much? Into just 0.5. So this is the concept of your void and the numerical portions. Okay. Another question is there given. A solid is formed by 2 elements. A solid is formed by 2 elements, that is P and Q, and the element Q forms a CCP, cubic close packing, and the atoms of P occupy 1/3 of tetrahedral voids. Okay, so in this case we have P and Q. The lattice or crystals are formed by P and Q. So for Q, the number of Q forms QB close packing and forms P occupy 1/3 of tetrahedral void. So for one atom of Q, tetrahedral void will be how much? 2, and octahedral void will be 1. So P will occupy 1/3 of tetrahedral void. That means 2 into 1/3. So what will be the formula? That is P23 and Q1 per Q. So it will be P2Q3. So that will be this type of question can come depending on this concept of void. Now the next question is, if NaCl is doped with 10 to the power minus 3 mole percent of SrCl. NaCl was there doped with 10 to the power minus 3% mole of SrCl2. That means then the question is number of cationic vacancies is, you have 4 options. Okay, option A is 10 to the power 5 mole inverse, option B is 6.02 into 10 to the power 20 mole inverse, option C is 6.02 into 10 to the power 18 mole inverse, and option D is 6.02 into 10 to the power minus 18 mole inverse. Okay, so the question is, NaCl is doped with 10 to the power minus 3 mole percent of SrCl2. So we need to consider that Na has plus 1 charge and Sr has plus 2 charge. So when one Sr2 plus can occupy or doped in the crystal, then 2 Na plus should be removed to maintain the electrical neutrality. I repeat once again, one Sr2 plus when come in the crystal, to maintain electrical neutrality, 2 Na plus will be replaced. That means how many cationic vacancies? Cationic vacancies become 1 because 2 atoms are replaced, but one position is occupied by this. So cationic vacancy is created by 1. That means 10 to the power minus 3 mole percent. So it would be like this. So 10 to the power minus 5 it becomes. Now in 1 mole how many atoms are there? 1 mole Avogadro numbers of atoms are there. So in 10 to the power minus 5 mole how many atoms will be there? It will be 6.023 into 10 to the power 18. And these atoms, that means these vacancies, because one Sr2 plus can make 1 cation vacancy. So the answer is option C. So this type of questions are very, very important for your board and competitives. Okay. So to get more updated videos, don't forget to subscribe and please like and share as much as you can.